interface design, and this is pretty much putting pixels on screen. Two examples of which you can see here. So if our goal is working towards explanation interfaces which maximize interpretability and minimize bias, which I assume we all do, we need to have or gain a very good understanding of the mental models that XAI users have of the explanations or the machine advice that we present to them. And researching this is at the core of our work. So in our research, we very much focus on the visual representations of explanations and how they affect decision-making behavior. And since we're doing applied research, we're most of the time are in the domain of digital health and clinical decision problems. So here in this example, I will mostly talk about work that we did with a study where we focused on the kind of usual diagrams that would come with explanations. So in this example, the diagrams that you might know from line explanations. And our goal is to systematically produce design alternatives for these kind of representations, and then to empirically evaluate these design solutions as to make statements about which designs would work better in a given situation. So our contribution in the paper for this workshop is that we present two approaches, which we call top-down and bottom-up. And these are two pathways towards developing such alternative design solutions. So these two approaches shall systematically establish design rationale. And design rationale is the reasoning and argumentation that underlies the activities that take place during the design process. And there's generally a need for more design rationale, not only in XAI interface design, but generally across information design. And we want to contribute to making the design process, so the decision-making that happens along the way of crafting these interfaces, more transparent, and through that learn more about how to design these novel kind of interfaces. So our goal, if you will, is interface design grounded in empiricism and taking more informed design decisions. So the first approach that we call down is about deriving design patterns that will tell us more about how to actually arrange information and explanation elements on the screen by analyzing the state of the art. So this would be the classical scholarly approach. Here we would perform a systematic literature review, and through means of coding, developing a design space which tells us about which elements would be used in interface or explanation interfaces as being published in the research body of knowledge, if you will. And in this example, we consider that the user knowledge, so to say, is baked in these interfaces, which have also gone through scientific evaluation. So this would be the top-down approach. And the other approach that we are very much focusing, we call this the bottom-up approach. And this is about deriving design patterns and understanding mental models by going through design activities with users. So this would be more the co-creation or co-design approach, where we have people perform decision tasks and giving them explanation, and then together with them, through the means of co- and participatory designs, develop alternative design solutions, and then searching for patterns in these design solutions, so that this would then allow us to also construct design spaces that are directly informed by user knowledge and making this implicit knowledge tangible for us. And to give you an example how this would look like at the end. So the result of the top-down approach, if you will, is first after conducting the literature review, that we construct a design space that would probably or most likely take form as a morphological box that would then allow us to craft different design concepts that are informed by the best practices or the things that worked in these other interfaces, and then developing new design solutions, which we could then test in user studies. And a similar thing is done with a bottom-up approach, but here we rather are looking for patterns in the sketches that we get from our participants that we had in the co-design sessions, and from the patterns that we observe there, so from making explicit how these people perceive the explanations we present to them, we would then also construct different design alternatives by means of coding and rearranging them as new designs, as you would see here on the right-hand side, as alternatives to the original diagram presentations, which we would then use as treatments in further user studies. But this would go too far. An explanation of how we then use these design things we have you can find in a late-breaking work paper that we also have here at Kai that would more elaborate on the process of the performing the user studies. So in a nutshell, we propose two different approaches that would come from two sides, so to say, to more systematically derived design solutions that make the design process a little bit more transparent, rather than saying that designs were developed in workshops, but really informing the community about certain designs could systematically be produced. And with this, at the end of my talk, and I thank you very much.
So hello everyone, I am Sahil Verma. I'm a PhD student at the University of Washington, Seattle, and I'll be presenting this paper which talks about the challenges in operationalizing counterfactual explanations in industrial setting. This work was done in collaboration with John and Keegan while I was interning at Arthur. So counterfactual explanations are an emerging technique under the wide umbrella of explainability research and machine learning. So given a data point and a model, a counterfactual is a data point close to the given data point, but has a different prediction under the given model. So in the figure on the right, you see there's a blue colored data point X, which is in the which has been classified by a model in the negative class. And there are two counterfactuals in red and green, which are classified, which are close to the data point X, but in the positive class. So as one can see, counterfactuals might not be unique, and therefore they might have different properties. And there are different properties of a counterfactual, which we'll see in a second. Counterfactuals are helpful in answering questions like, what minimal change do I need to produce in my features so that when I come to the bank 6 months later, I'll get the loan? Counterfactuals were recently summarized in two survey papers, which we have listed on the slide. There are several desirable properties of counterfactual explanations. For example, they should consider the actionability of features that they are suggesting to the users to modify. They should not, for example, they should not suggest someone to modify their place of birth. Counterfactual explanations should also adhere to the causal relations between different features and respect the data manifold. This is an assumption that the training data for the model has all the feature correlations and feature distributions that are present in the real world, and therefore any counterfactuals which is far from the training data manifold is probably not attainable. Counterfactuals should also should be sparse, in the sense they should only suggest changes to a few features and not all the features, and this adheres to the principle that was put forward by Tim Millers in his paper, which said that small explanations are more understandable to the people. The last two properties are about the processes that are generating counterfactual explanation. They should be model agnostic. They should be able to generate counterfactual explanation for black box models, and should have amortized inference so that once the approach is trained, it can generate counterfactuals quickly. So there are several challenges in the industrial adoption of counterfactual explanations, and we will contextualize them in the with respect to the properties that we just saw on the last slide. The first problem occurs with operationalizing causality in counterfactuals. So for causality, you need something like a structured causal model for the data sets for which you're generating counterfactuals, and that does not happen for most of the data sets that are present. Even if we want to learn the causal model from the given data, it is not possible because the data that's given to ML practitioner or modeler is static. It's not interventional data which they can use to learn the causal relations. There are also problems due to the real world dynamics. For example, the machine learning models that are producing the decisions are not static, and therefore the counterfactual that was prescribed might not be a valid counterfactual 6 months later. There are problems due to the individuals that are being prescribed the counterfactuals not being able to follow the advice. For example, if you suggested someone to change a job so that their income increased by $5,000, that might not happen. Their income might only increase by $3,000, and therefore you might need to go back and forth with the individuals so that you can reach a counterfactual state which is a valid counterfactual and easily attainable by the individual as well. There are problems due to biases in the real world. For example, the counterfactual explanations, the machine learning models that we are being used might have demographic biases against a particular gender or particular race, and the counterfactuals generated yet do not consider this. They should consider it. There might be personal biases of an individual that you're prescribing the counterfactuals to. For example, for someone, it might be easier to change their job than their home city, and therefore counterfactuals should take that also into the account. There are problems which are lacking due to the collaboration and in different research communities. For example, there is a lack of unified vocabulary within the XAI research community about counterfactual explanation. Like there was a recent discussion before Europe's, which was like several people wanted to call counterfactual explanations as contrastive explanations, and the difference over there was basically the presence or absence of causality. So addressing that would be important. There is also lack of acceptance of counterfactual explanations by regulatory bodies, and we hope that would be aided with collaboration with the legal community. There is lack of visualization for counterfactuals from the perspective of the end users. We hope collaborations with the HCI community can aid in this problem. And lastly, most of counterfactuals has been applied in the case of classification problems. We would like to see how can counterfactuals be applied in the case of regression problems. And we hope machine learning community collaborations help in this particular issue. Thank you for listening. I'll be happy to answer any questions, and feel free to connect with me on Twitter or email. Thank you.
So hi everyone, thank you for being here. And my name is Shen, and I'm a PhD student from the Penn State University, working with Dr. Huang, who is also here. Today I will introduce our work titled Explaining the Road Not Taken. So as we know, the XAI studies in natural language processing, named NLP applications, are growing rapidly. But from a human-centered perspective, it is unclear to us whether existing NLP XAI studies respond effectively to practical user needs. Meanwhile, XAI Question Bank captures the practical user needs using prototypical user questions. They categorized all these questions based on the XAI algorithm types, such as how does a system work globally, or why does a system not work in this way? They further verified all these questions with AI product UX designers for real-world user needs. So this leads to one interesting problem to us. How well can existing NLP XAI research respond to these questions? For addressing this problem, we surveyed 218 NLP XAI papers published from the top-tier NLP venues within 5 years. But how to match over 200 papers with 43 user questions. Well, the way we came up was to summarize a collection of HCXAI forms which visualize different types of explanations. Then we used them to cover over 200 papers on one side and match user questions on the other side. For each, particularly for each HCXAI form, we gave it a formal definition and collected typical user questions it ever addressed. Then we use these 12 HCXAI forms to compute each user question's attention. For example, here, when the users are interested in how does the system make predictions globally, we can use decision trees to explain the model's reasoning process. Or we use the executable rules to explain the model's logic. Or we just show what inputs the model has seen during training for the users to understand the model. Thus, we can collect all forms that can answer this specific user question. For each form, we also annotated all the papers which explain using this form and computed a form weight as the percentage of all associated papers among all the surveyed work. Note that when one paper has multiple forms, we divide it into equal fractions, summing up to 1. Finally, we sum up all applicable HCXAI forms weights to be the user question's attention. As a result, we got this heat map of HCXAI question bank, which intuitively visualizes how many % of all surveyed papers can address each user question. When the question's color is darker, it means more papers have answered it. From which we can see 9 out of 43 questions are about how AI system can provide specific predictions, where many papers already answer them pretty well. In contrast, there are 16 questions inquiring about what AI cannot achieve, such as why is this instance predicted as P instead of Q, or why not using these features or data, where we see much fewer papers have answered them yet. Overall, we find that users are interested in explanations for the road not taken, namely why AI chose one prediction instead of a legitimate counterpart. Although currently the NLP HCXAI studies cannot address them well, we've seen more counterfactual explanations emerging since here, and hopefully we will generate more of these explanations to address the user needs. Well, finally, we would like to invite you to check more findings and discussions in our paper. You can also visit our website where we open sourced all the surveyed papers with detailed form annotations. Thank you for your time and attention, and we look forward to your feedback and discussion.